So this class has involved studying a few different types of load. One of them is called axial loading. So you take a member and you try to stretch it longer or push it shorter. That's axial loading. We've also done flexural loading, which basically is taking a member and seeing if you can sort of flex it, right? You can kind of make it a smiley face or a frowny face, but you can flex a member. And then the third kind is torsion, right? So we've gone through all of those. And those represent a really, really large chunk of the kinds of loads that are applied to various kinds of members. But there are a few other kind of special cases as well, and we're going to touch on one of those special cases today. The special case we're going to look at today is essentially the stress that is induced in members that have to carry some form of internal pressure, all right? And so these members that are designed to try to carry an internal pressure are known as pressure vessels, right? And we are going to specifically today look at what are called thin-walled pressure vessels. And so I'll tell you, first of all, like, what do we mean by thin, okay? It can be shown that as long as you have a ratio of the radius of one of these pressure vessels, which, by the way, we're going to constrict our discussion today to two shapes. One is spherical pressure vessels, and the other is a cylindrical pressure vessel. Both of these have radii that are associated with them, right? So you take the radius over the thickness of the wall, T, and if this is greater than 10, then that means that we are talking about a thin-walled pressure vessel. And as I was about to say a minute ago, it can be shown that as long as the radius over the thickness is greater than 10, then you're going to end up with less than about 5% variance in the amount of stress that will occur across the wall of a vessel that's built like this, right? In other words, you have nearly constant stress that will be induced in the walls of a pressure vessel where the radius over the thickness is about 10 or more, okay? So that's what we're talking about today, is this idea of thin-walled pressure vessels defined in that way, okay? And they're designed to carry this internal pressure, okay? So I'm going to go ahead and say this, too, for our discussions today. I'm going to be talking primarily about the internal pressure. This internal pressure, we can think of it as being, for the most common cases, we can think of that as being like a gauge pressure, meaning the amount of pressure that we have inside the vessel relative to what it is on the outside of the vessel. Now, I have to kind of qualify that just a little bit. If you're dealing with ambient conditions such that they have really, significant external pressures, then sometimes you have to modify these equations a little bit or modify your method a little bit. But as long as you're talking about something like just atmospheric pressure, that's typically pretty small relative to the kinds of pressures that we're talking about, and so we can basically kind of ignore it, and instead of thinking about there being an external pressure and an internal pressure, we can just think of the internal pressure as being the gauge pressure, meaning the difference between the internal and the external pressures, okay? So that's what we mean by internal pressure. And what we're going to do today is study this spherical shape and this cylindrical shape, and my goal with this is not so much to just teach you a couple of new equations. One of my goals is to let you guide me through the process of coming up with the formulas that we should have for either the spherical pressure vessel or we'll do them each. We'll do the spherical first, then the cylindrical, but you've seen me in several cases throughout this course. You've seen me look at a situation and then try to take it apart in a way that we can derive a formula for certain types of stress or other things, right? And I want you to help me do that, but I want you to kind of drive, all right? So can you guys help me with that today? I see some trepidation, some fear, all right? Don't be afraid, because it's not that bad. In a lot of our cases where we've derived formulas for stress, one of our first steps is to what in a lot of those cases? Okay? Okay, what we have is we have stresses are kind of like internal forces, right? And we have this really, really awesome tool of using free body diagrams to come up with unknown forces, right? So that's a really strong tool that we can bring to bear on something. But a free body diagram has to have external forces that are the things that you're trying to find. It doesn't do very good for finding internal forces unless you do what? How do you make an internal force inside of a structure into an external force? Okay, I think I heard someone over here say, make a cut. Okay, so what we have there, we'll start with the spherical side. We've got this sphere that is carrying pressure inside of it, right? And what we'd like to do is make a cut in that sphere so that we expose the stresses that exist in the wall of that sphere as external forces to our free body diagram. So where do you think you might like to make a cut? Let's try to make it as easy as possible. Right through the middle, right? You, like you're taking a knife and you just slice right through the middle of this spherical pressure vessel. So let's actually make a little sketch of that. Right? Let's say I take a plane, something like this, right? And I kind of cut through the middle of this thing, and as I do, maybe it will cut through shape something like this, right? As it cuts through the middle of this pressure vessel. And once I've made that cut, I'm going to draw a free body diagram of just a portion of it, right? So let me go down here and draw a free body diagram of just the left half. Right? So it's going to look something like this, right? And then it's going to have a certain wall thickness to it. Okay? So far so good. We've cut the thing in half. So what sorts of influences happen on this half of this pressure vessel now that I've made that cut through the middle of it? So you have internal pressure. Now let me look at the internal pressure, because there's a couple of different ways we can think about the internal pressure. One of the ways is we can think of there being, and I'm going to kind of do a double section here, right, where you kind of look at it this way. One of the ways you can look at the internal pressure is that anywhere that it's pressurized is going to have a kind of a little force locally that's normal to the surface all the way across like that, right? That's going to end up being a little bit complicated, although it's something we could do if we exercised all of our skills in calculus and everything that we've come up with that you've learned so far. But we don't even have to do that, because let me show you what else we can do. We get to define what material is part of our free body diagram and what material is not part of our free body diagram, right? So let's be a little bit creative here and say, inside of this pressure vessel is the fluid that is under pressure, right? And if we think of it as being a gas, it's probably the easiest way for us to think about it, so we don't have to try to think that there's a difference in pressure throughout the depth, right, of it. So let's think of it as being a gas, but let's think of that gas and it's pushing against the side, but we could actually include that material that sort of occupies the cavity of this thing. We could include that as part of the free body diagram, right? You could say that gas that's contained by this pressure vessel is also part of the free body diagram. And if so, then what we can do is we can say, well, there's pressure acting on that face of that gas. And that makes our shape of this distributed kind of pressure, right? It makes it a lot easier for us to figure out. Okay? That actually is the internal pressure, P, that's pushing against that surface. Well, what is it that keeps that gas that's contained inside of this thing, which, by the way, I could draw that here, kind of say, here's the gas that's inside of this diagram. And I'm showing that there's this, pressure that's acting on that face of that gas all throughout that face. It's hard to draw, but it's, imagine it being distributed all across that whole face. Okay? Well, what if that was the only influence that was happening on this half of the free body diagram, then what would the free body diagram do? Or what would that body do if that was the only influence happening there? It'd probably want to accelerate to the left, right? Yeah, so there's got to be something that reacts against it. And what is that thing that reacts against it, you think? The stress in the wall, right? So reacting against this is a stress that happens here in the wall that kind of goes the other way, right? And it's distributed along the entire face of that wall. Something like this. Okay? And so this is our diagram, and let's go ahead and put a coordinate on it. Let's say that this direction right here is my x direction. Okay? I could put my other directions on there as well, but I don't even really care about those very much. Okay? So if that's my free body diagram, right, then what do I do with a free body diagram? Okay, we've freed the body. I agree with that. Shall we put some more information on here? Let me label this and say this right here, this is the stress in the wall. I'll just call it sigma. The stress in the wall of that free body diagram. And the pressure here in the middle, I labeled it up there, but we'll call it P, right? That's what we know so far. But what do we do with free body diagrams? We do equilibrium equations, right? Sum forces. So how do I take this body and sum forces? Along the x direction is probably what makes sense, and I can, maybe, I'll just point it that way and say that's positive. Okay? Do I have forces being applied to it on my figure? Kind of, right? I have something that's very closely related to force because I've got pressure and I've got stress. So what's the relationship between pressure and stress? Pressure and stress are measured in the same type of units, right? It's always going to be force per area, right? Because stress, for instance, is equal to force over area. In order to do a sum of forces, I need to get this thing in terms of forces. So how do I do that? Okay, force is equal to stress times area, or in the case of the pressure, it's the same thing. Force is equal to pressure times area. Right? That's how our forces are related. So when I populate my sum of forces in the x direction, how do I do that then? Okay. So we need to know the size of this thing, and actually, I guess I didn't put that right up here at the top. What is it we'd need to know? Well, let's actually express it in terms of, think of a radius to the outside or to the inside wall of this thing, which, by the way, since it's a thin-walled pressure vessel, we're not going to try to go to the level of thinking of what the radius is to the inside versus to the outside. We're just going to kind of think of this radius as being the radius of the vessel, right? There are some interesting things you can do there, but for our purposes, we're not trying to get it super fine level of detail. We're just trying to get the basic idea. So let's say that that's the radius value of this pressure vessel, R. How is that useful for my sum of forces here? Okay, let's do the internal pressure first, right? The force caused by the internal pressure there is going to be minus P times what? times pi times r squared. I'm just taking the area of the face of the gas that basically this pressure is acting against. Okay? Now what about stress? Plus, there's a couple different ways that we can do this. Let me show you the easiest way to think about it. And this works because it's a thin-walled pressure vessel. But think of this area that the stress in the wall acts over, right? That's this area right in here. And you might remember that when we did our derivation of polar second moment of area, remember what we did to find what that little dA was for that little ring? We made a slice, and we imagined stretching that slice, kind of unwrapping it off of here. That's probably the easiest way for us to incorporate the information about the wall thickness T that I put up here, right, is to think of unwrapping that. And if we do it that way, then what would the area be for the wall of this pressure vessel? Okay, and it's based basically on like unwrapping this thing and saying it's got a thickness of T and at an effective length of 2 pi r after we've unwrapped that little area from, you know, how it extends around the circumference of this thing. Okay? So, let me erase that again and say we've got the stress times 2 pi RT. And those are my only forces that act in the x direction. Therefore, I can take this and try to solve it for sigma. Okay? If I do that, then what I'm left with, okay, is going to be equal to P times pi times r squared over, in the denominator I'm going to end up with 2 pi r t. Okay? And what can I do with that? Okay, the r cancels the r. Pi cancels the pi. And what am I left with? Okay. And since we followed very carefully what the process was of looking at, finding this stress, I'm going to say you can either memorize that or you can remember what we did and do it again if you need to, right? But you're going to need to be able to find the stress in the wall of a spherical pressure vessel. Okay? Any questions on that so far? Yeah.
Does this change as you move, like we cut it in half, so does it apply no matter where we cut it?
Okay. His question is, does it apply even if we hadn't cut it in half, right? Would it still apply? I would say cutting it in half is the easiest way for us to only have to deal with one direction of force, right? If you make a cut other than just right through the middle of it, cutting somewhere else is going to lead to a more complicated nature of the forces that exist between the two parts where you made the cut. But because of the symmetry that you get when you cut right through the middle, it allows you to use logic and say that there must only be one component of stress that's happening there, and it's got to be normal to the face that we made the cut on. So it makes that a lot easier by making the cut right through the middle. Having said that, a really good point to make here is it didn't matter what direction I made my plane go on my very first cut through there, right? I could have made that plane just as easily. I could have made the plane go this way, right? And made a cut maybe that looked something more like this. As long as it goes right through the middle, I don't care what direction that the plane's cut, I would come up with the same result. And this is actually very interesting because I'm going to go ahead and point out that that means that if I took a little patch of material on the surface So let's say I imagine there being this little patch of material on the surface of this spherical pressure vessel. Right? I kind of cut out a little patch like this. What are the stresses that are acting on that little patch of material? Right? You're going to have a normal stress acting this way, but you'll also have a normal stress acting this way. What are the values going to be of those stresses? PR over 2T in one direction, but PR over 2T in the other direction as well. All right? And this is actually our first time in this class where we've actually come across something that is more than one component of stress at the same time. All right? This is called a state of biaxial stress. Now, having said that, I will kind of expand on that a little bit and say, even though it's a state of biaxial stress, it doesn't mean that our conclusions are going to end up any different than what we would have thought about things like, what is it going to take to fail this material? Okay? And we're not going to get into all the theory of it, so for right now I'm going to ask you to take my word for it that the failure criteria that we use for materials, that the job of those failure criteria is to try to take into account these multi-axis states of stress that material could be under. For this particular state of stress, where it's got the same stress pulling in two different directions and no other stresses, when that's what we have, then we will still predict failure according to whenever that stress reaches our yielding stress, for instance. Right? That part won't change for this type of stress. But that's going to be the topic of coming courses, is what if you have a more complicated state of stress than this? How do you figure out how close you are to failing that material if you have a more complicated state of multi-axial stress? Okay? So that's kind of preview of coming attractions. All right, good job. You guys figured out what the stresses were. And really, there's just one stress that we had to figure out for a spherical, thin-walled pressure vessel. Okay? What do you want to do next? Shall we do the cylindrical one? I mean, since it's so nicely drawn up here and everything. All right. So what do you think we should do first for our cylindrical pressure vessel? We're going to make a slice, right? And we actually might have to make more than one slice. Okay? Let's start with a couple of slices here, okay? We need to be able to kind of isolate stresses that might be happening in more than one direction on this body. And so let me actually say this. Have you ever seen a pressure vessel that's cylindrical in shape? Have you ever seen one fail? Like pressurized up to the point where it bursts? Okay. Have you ever dropped an aluminum can? Like a Coke can, right? You drop the can, and when it hits the ground, it busts open. Does that ever happen to anybody? Okay. When it busts open, have you ever looked at the failure location where it busts open? What shape is it? Okay, it's a straight line, and where does it typically occur? Right down the kind of the height of the can, right? It's kind of along the long axis of the can. That's a little bit of a clue to us, and it might say maybe the stress is pretty bad in that direction. Okay, so why don't we set one up to where we make a slice through our cylinder so that our slice exists. Okay, I'm going to kind of slice through with a plane like this, right? And the slice exists such that it cuts right through the material in a way that it would sort of replicate that direction that you see it wants to fail anyway, right? And so as I slice through the middle of this, you can kind of imagine it slicing, you know, along the edges of this, okay? And that's one of the cuts that I'm planning on making. But it's not the only one. Because the other thing I want to do is I want to ignore the effects of these things on the ends that are called end caps. All right? End caps are a little bit different. And they get a little bit more complicated if we have to really try to figure out the true stresses that happen on the end caps. So what do you think I might want to do for now, where all I'm trying to do is look at what's happening in the cylinder itself? How about we just slice them off, right? So imagine taking a plane something like this, right? And as I do this, it's going to end up slicing off couple of little chunks of this thing so that I slice off those end caps. And now what I'm going to do is take the piece of material that's to the rear of where those cuts are made right there and try to draw it separate from the rest of the material. Here's what it would look like, right? Something like this. Okay, I sliced off that little piece, all right, and what sorts of forces act on this little piece? Okay, so let me do the same trick I did before and include the contents as part of my diagram. Okay, so let's say those two lines right there represent also kind of the boundary of the material that's actually contained in the pressure vessel. Right? So it's also part of my figure. And what happens on this face that's facing us of that little green thing? What's happening there? Okay, there's going to be some force that's happening on this face. Again, it's hard to draw so that it makes it clear, but we're going to say all over that face we have this kind of distributed pressure happening all over that face. Okay, so that's my P. And if we didn't have something else acting on this body, then that would drive that piece to go into the page, right? But what else do we have acting on the body? Okay, we have some stresses that are going to act, they're going to counter it by coming this other direction, acting in the wall of the pressure vessel. Like that. So we got the P and we've got the stress that's happening here. Okay? Now, we have a couple of different, because we don't have the same level of symmetry on the cylinder as we did for the sphere, we're going to have a couple of different directions that we have to evaluate. This was the first one that I kind of tried to get you to think about based on the Coke can that's going to split up the middle. I'm going to go ahead and give this a name. I'm going to call this sigma sub h. And the reason I'm calling it sigma sub h is that another name for this thing is hoop stress. Okay? And here's how you can think about hoop stress, actually. So hoop stress, a really good picture of this is you might have seen old-time barrels. Matter of fact, I've got a picture over here. You might have seen old-time barrels like this. And if you fill up a barrel so that it's containing pressure, what is it that keeps the slats of the barrel from kind of blowing apart? It's the hoops that hold this pressure in this way. And this is a really good mental picture of what kind of stress we're talking about with sigma sub h. It's the stress that sort of keeps this pressure vessel from bursting, like our Coke can that we talked about a second ago. Okay? But it's the same thing as what those hoops on a wooden barrel like this have to hold together, because the slats of the wooden barrel aren't really held together by anything else besides this hoop that holds it all together. All right, so I've given it that name, sigma sub h. Now what? If you want, we can put some directions on here. How about we put some directions like this? What do you want to name these different directions? Let's say we call this one x. Let's call this one here y, and this one z. Okay, so there's my little free body diagram. What do I do with it? Okay, equilibrium equation again, right? We're going to sum some forces. What direction? In the y. Okay, and what sorts of influences do I have acting in the y? I've got stress, so I've got that hoop stress multiplied by what? Because stress by itself is not a force, right? I've got to multiply it by the area over which the force acts. So let's go ahead and, because we don't necessarily know what this is yet, let's go ahead and give it some dimensions. Let's say that I chose to do this over a length of L, right? So that means this length right here is L. Okay? I didn't draw it on the very first picture, but let's again say that it has a radius of R, right? So let me go, I guess I'll put it like this. Say this is a radius of R for this cylindrical pressure vessel, which means that that's also this dimension right here, R. Okay? I did put up here that the thickness of the wall of the cylindrical pressure vessel was T. So I can put that on here and say this was T, that thickness up there, and then that's also replicated down here. Okay, so given those dimensions, what area does sigma h act over? Okay, so we say 2 times L times T. I think I heard someone say, right? So this is going to be multiplied, times 2 times L times T. Okay, the 2 because I have 2 different faces, right? I've got one up here, and I've got one down here. Okay, and that's acting in the positive y direction. Then what? Minus P, and what area does that P act over? Okay, 2 times R, because that's what gives me the total length across this whole thing, right? 2R times L. All right, set this equal to 0. And what do we have for sigma h? Okay, 2 PRL over 2 LT. 2's cancel, L's cancel. So what does this give me? PR over T. Some of you might be wondering why I'm drawing my P's very weird. I'm trying to not give you the idea that it is rho or something else that looks like a P that we've done in the past. I'm doing kind of a scripty looking P. Anyway, if that annoys any of you, I apologize, but I'm trying to make the character look a little bit different for internal pressure. All right, so that's PR over T as opposed to PR over 2T. That's interesting, right? So if what you're telling me is that if I have a spherical pressure vessel with a particular wall thickness and a particular diameter to it, right? it's going to have half the stress in it as a cylindrical pressure vessel has in this hoop direction, right? With the same exact wall thickness and the same diameter. That's an interesting result, okay? But, so a lot of you probably are ready to say, well, is there another direction of stress? Okay? For our other direction of stress, let's do our cuts a little bit differently. Okay? So for my other direction of stress, instead of having this cut that we make down the length of it, and instead of doing two cuts like this, for our other question of a direction of stress, let's just leave one cut, right, and do a free body diagram of one end, including the end cap. Okay? So what that would look like, if I was to do a free body diagram, it would look something like this. Right? We'd have this thing cut off. It then would go over some distance, and then we would have this end cap on here. Okay? And remember, we're going to do again, we're going to actually let the fluid that's inside of the pressure vessel come along with this this drawing, which means that we have a face right here that is experiencing this pressure. Something like this. And what reacts against that pressure? Stress in the wall, right? Coming back this way. All the way around on, you know, the perimeter. Ends up being a lot of mess there with my figure, but you get the idea that the reaction that happens there happens in the wall. I'm going to give this thing another name. Instead of sigma sub h, I'm going to call this one sigma sub a, right? Sigma sub a is called axial stress. Now, we could go through a kind of more formal process of figuring this out, but have we figured out anything that looks like this case of axial stress? Have we figured anything else out that looks just like that already today? That isn't different than the sphere, right? Like functionally, we're talking about the same way that the cut is made. We're talking about the same internal pressure that's happening on the gas. And so we're going to come up with the same conclusion here and say that sigma A is just going to be equal to PR over 2T. All right? So now let me ask you the question. Why did the Coke can split down the middle from the bottom to the top along a pretty much a straight line when you dropped it? The stress is double in that direction than this other direction. So it makes sense that it would split along that direction because you've got twice the amount of stress. All right? So that's kind of a cool outcome that we've been able to see. Our hoop stress is going to be double the axial stress. Kind of to mirror a similar thing we looked at just a second ago, if we look at a little element of stress on the surface, let me not make it red here. If we look at a little element of stress on the surface of this pressure vessel, right here, right? What are the stresses that act on that member now, or on that little element of material? In this direction, I've got hoop stress. In this direction, I've got axial stress. Okay? And let me go ahead and tell you about this one too, because this is another state of biaxial stress. All right? And you're going to cover some theory here at some point in your schooling where you figure out how do you deal with more than one component of stress? How do you know when it's going to fail? I'll go ahead and tell you that for a biaxial state of stress like this, where you've got both of them in tension, which they both will be, right, for this little element of material under this load only, both of those directions are going to have tensile stresses in them. When that's what you have, the larger value will control and the smaller value won't matter. All right, so we'll just go ahead and say that whenever sigma sub h gets up to a level that would cause it to fail, we're going to say that the material will fail, at least for right now. Again, I'm giving you a preview of coming attractions. There's going to be a lot more detail that goes into figuring out multi-axial states of stress. For right now, just take my word for it and say that hoop stress component is the one that's going to control when this material actually fails. Yes, sir.
Whole vessel fails.
Okay, I'm really glad that you brought that up. Basically, what he's getting at is he's saying this is probably going to be a uniform kind of material that this thing is made out of, right? It's going to all have the same material properties to it, and because of that, once the hoop stress gets up to the level that would cause it to fail, the whole thing's going to fail. It will have failed in that direction before it could have failed in the other direction anyway, right? So that's kind of what you're getting at. I'm really glad you brought that up because that is true as long as the assumption you said right at the beginning holds, right? If the material is what we call isotropic, you know what that means? Okay. It means that it has the same properties regardless of direction. Right? If it's isotropic, it means it has the same properties regardless of what direction you're looking at in the material. Not all materials are isotropic. Okay? We probably wouldn't have the word isotropic if there weren't some examples of materials that were not. Right? Anisotropic is the opposite of that, saying you have different material properties in different directions. Give me an example of a material that's anisotropic. Wood, someone says, is a really good example. So if you have wood and you pull it along a direction of the grain, is your wood pretty strong? I mean, if the grain runs this direction and you try to pull it axial along that same direction, your wood's going to be pretty strong, a lot stronger than if you take the wood and let the grain run opposite of the direction that you're trying to pull. It's going to split that wood a lot more easily in that direction. So a wood is a really good example of an anisotropic type of material. And you might even notice that in the reference material, as a matter of fact, I've got it up right here. Look at what they have listed for wood. Down here it says all timber properties are parallel to the grain. Right? They had to specify that very carefully because they're saying these are not the properties if you go perpendicular to the grain of the wood. Okay? A lot less, yes. All right, so let me give you another example of an anisotropic type of material that this might actually come to bear on. I thought of this actually on my way to work. I play tennis, and I happened to have a ball or a tube of balls in my truck. And it's made of plastic, right? This is kind of a cool thing because I've got this cylindrical pressure vessel here, right? It's got pressure held inside of it to keep the balls fresh. And inside of there, I've got the balls, which are spherical pressure vessels, right? So that's kind of cool. I've got both of them right there in one package. But the reason it came to my mind is that plastics are interesting materials because plastics, and by that I mean polymers, right? Polymers are interesting materials because they can actually be prepared in a way that they are stronger in one direction than another, right? As a matter of fact, by stretching, if you plastically deform a polymer in a particular direction, it will typically get stronger in that direction that you've plastically deformed it. It lines up all of the little polymer chains in that direction, and it makes it stronger in that direction. So if I was going to design one of these ball cylinders here so that it had the right amount of strength in the hoop direction as well as the axial direction, what would I want to do maybe? One way you might be able to do that is you might be able to initially manufacture it a little bit smaller diameter than it needed to be and then do a manufacturing process where you stretch it out up to the diameter that needs to be, and that would get all of your material stretched out, and it would be stronger in that hoop direction than it would be in the axial direction, and maybe you'd be closer to being sort of the same amount of factor of safety, so to speak, in the hoop direction as you would have in the axial direction. It was just a thought that I had as I was coming to work, so I figured I'd bring the tube of balls in and talk about it. So hope maybe that helps. But you're actually not wrong in saying that a lot of our materials are isotropic. And if so, if they're an isotropic material, you will expect that the materials will typically fail first, kind of in that hoop direction. All right, shall we do an example? All right, here's an example. Here we have a spherical pressure vessel composed of annealed red brass. We're going to install a cold rolled red brass port as shown. Okay, first thing we're going to do is find the maximum pressure that the spherical vessel can hold while maintaining a factor of safety of 2.5 against yielding. Okay? At that pressure then, we're going to figure out how thick we need to make the inlet and outlet port that we're installing on here so that we keep the same factor of safety for that as for the rest of the vessel. Okay? So we're going to again get a factor of safety of 2.5 against yielding for the port as well as for the rest of the vessel. Okay? So what do we need to do first? Okay. Do we need a free body diagram? We could if we want. We could make another cut. We could rederive our formulas again, but our formulas are derived for basically a spherical pressure vessel, right? So we can just use the formula as is. I'd say one of the first things we need to do is look up some material properties for this red brass, right? So we need to go into here and say red brass annealed 15. Let's make sure we know the units. Okay, for the elastic strength in tension, we're talking about 15 KSI. Okay, for that annealed red brass. Okay, and we might as well get the cold rolled one while we're here. So 15 versus 60 for the cold rolled. Isn't that cool? Like you can really increase the yielding strength of red brass by doing a process called cold work. Right? We won't get into all that, but that's an interesting thing. This is the same material, just prepared with no cold work versus with some cold work, and you can increase the amount of strength by a pretty good bit. Okay? But anyway, so we've got 15 versus 60. Let me write that on the page right here. Okay? For this part right here, our yielding strength is going to be 15 KSI. Versus this part up here, the yielding strength is going to be 60 KSI. Okay? Then what? Okay, spherical pressure vessel stress equation. Internal pressure times the radius over 2 times the wall thickness. Okay? So for us, this is like working stress, right? This is the stress it's actually experiencing. What do I need to do if I want to kind of imply or kind of include this factor of safety? Okay? Basically, I need to take this working stress, and instead of, saying, basically what I'll do is this, is I'll take this working stress and set it equal to an allowable stress, right? Allowable stress is the stress that we assume will cause failure divided by the factor of safety, okay? So we take this and we say the stress that causes failure is 15 KSI. If we divide that by the factor of safety, we can set it equal to the internal pressure that it should be able to carry, right? Multiplied by the radius. What's the radius? Okay. Be careful of these. There's not that many things that can trip you up, on these problems, but radius versus diameter is one of the classic ones that, you know, can trip a lot of people up. So just be careful. Don't allow yourself to get tricked into, you know, putting a diameter in where you should use a radius. Okay, what do I put in the denominator? 2 times, you've got a 65 thousandths wall thickness. Okay? And out of this, we get that P is going to be equal to, I very quickly go to the equation solver on here, maybe too quickly. All right, when I do this, I'm probably going to want P to wind up in PSI instead of KSI. So what do you think I might want to do with my 15 KSI? Okay. 15 KSI is 15,000 PSI, right? So I'm going to go ahead and put in 15,000 for the 15 KSI. Down here I'll put 2.5. Okay. This is going to be equal to my x that I'm trying to solve for. Let me do it this way. The x I'm trying to solve for times, right, here let me do 3.5 over 2. And then the denominator I'll put 2 times 0.065. We'll solve for x. Okay. And x ends up giving me 445.7 PSI. Okay. So that is the answer to part 1 of the question that was asked. What's the maximum pressure it can hold while keeping a factor of safety of 2.5? We're going to say about 445.7 psi. All right, second part of the question is, at that pressure, how thick should the wall of the port be so that we can have the same factor of safety as for the spherical part of the vessel? All right, so what do we need to do there? Okay, yeah, so basically it's the same kind of a formula except for, in this case, it's going to be the hoop stress of that cylindrical pressure vessel that controls. And so its formula is going to be PR over T without the 2, right? So with this, we, again, you know, he said a second ago, we also need to use the material properties appropriate for this kind of material we're going to make that port out of. So we're going to say 60 KSI. We want to keep the factor of safety of 2.5. Set this equal to 445.7 PSI. Okay. What's my radius? Okay. So, yeah, 1/2 inch divided by 2, which is 0.25 inches. All this divided by, no 2 in this one, right? Just T. And that's what we're trying to solve for. Okay? So we'll go ahead and punch all this in. Let's say I've got 60,000 over 2.5. This is going to be equal to, all right, 445.7 times 0.5 over 2, and then this will all be over x. All right, and that gives me 4.643. So T, 4.643 times 10 to the minus 3. What should the units be on that? Inches, right? This is actually, since I converted this to PSI, it will exactly cancel out PSI over here. So it's just whatever the units were of my length up there is going to be the units that come out for T. So this is going to be in inches. Okay, that's not probably the normal way you would think of seeing an answer like that reported, so we'll kind of convert it here. We're talking about a thousandths or so, right? Wall thickness. Is that thin? Okay. Do you believe it though?
No.
You don't believe it? It's pretty thin.
And that's the minimum thickness.
Okay.
Right.
This is with a factor of safety of 2.5.
Yeah, so it won't even come close.
Okay. So what I want to point out with that is this. This is, we didn't do anything wrong. This is hypothetically, a pressure to hold 445.7 psi. All you need for this material at 60 ksi, this is all the wall thickness you need to hold that pressure. Okay? When you actually see pressure ports installed on actual pressurized things, do you think that they're designed only for the pressure that they have to hold? Okay? You typically assume they also take a little bit of abuse, right? So we might, if we were going to really design a port like that, it might not just be internal pressure that will concern us in terms of what could make that part fail, right? You just bonk it real hard with something. That's a technical term, right? You just hit it with something. It's going to end up failing it if it's 0.04 of an inch thick, right, or 4.5 thousandths or whatever this ends up being, right? It's going to end up, probably causing some damage due to that, even though hypothetically it can hold this pressure. Okay? Yeah.
When you attach it, you're probably going to weld it. Does that make it any?
So you're going to have to actually attach it using some actual method of attaching it. You'll braze it on, or you'll weld it, or something like that. That might have another factor as well, and I'll say we're not dealing with that. So we very well could end up with stress concentrations that occur at the location where it's attached on there. And we haven't really dealt with that at all yet, but it's another thing that we need to think about. Yes, sir. Yep. He says for this problem, it was told to us that we had the diameter to the inside of the sphere as opposed to the outside of the cylindrical piece, okay? And I will say that this was not our goal to try to delineate between those. We're planning on the thicknesses being very, very, very small relative to the overall size. So small that it makes almost no difference whether you measure it to the inside versus the outside, okay? Having said that, though, I think the technical answer should be that it probably makes more sense to think of your diameters being measured to the inside for what we did than to the outside. But, even our derivations sort of assumed that wall thickness was fairly negligible in size. Okay. All right. These problems typically are not very hard. All right. So, if you're looking at it thinking there's just not that many ways that these can be permutated, you're probably right. They don't typically end up being very hard, but make sure that you know the formulas and and how you can incorporate something like a factor of safety and material properties and that kind of thing too. Okay? All right. We'll call it a day.